There we are. Whoa, we got 3 people. Okay.
It's a little messy over here.
Yeah, the road's bad?
Yeah. A little bit.
Okay.
It's turning to slush now, but it still could be a pain in the butt. Going over the food line, I see a truck spinning tires just coming out of his parking space.
Uh-huh. Okay, so let me line this thing up. And let's see, before I forget, let's see, there's Sasha and Cody and Julianne.
Yes.
Okay. Oh, sign in. That picks up everything. That you see there. In case somebody else shows up. We still got 3 more missing.
I love those gates that you have behind you.
All systems are go. Great picture. Yeah. Yeah, let's call it up. Start this. Let's see. Should ask me to pick up my left arm. Yep. Calorimetry. See that a little better. Okay, that's everything. Maybe I'll get a little closer. That's got a reflection on it. Can you guys see that okay?
I can see it okay, but barely.
Yeah, it's not very good quality, is it? Maybe if I move it over, it's getting a reflection, I think. Can we pull that shade down?
It seems a little bit better.
We got a whiteout going on in here. That's better.
Yeah, I can see it a little bit better.
There we go. All you really need is to see enough of the slides so you can follow along on your hard copies. Okay, we're going to pick it up today where we left off, and that's with calorimetry. Calorimetry is a word that is derived from Latin, I think. Calor means heat, and metry means measurement. So it's just a method for measuring heat transfer, heat production, heat loss in a chemical reaction. Watch out for the cord. Okay, so one of the things we have to identify as part of a measurement is a specific heat capacity. That is, how much will the temperature change for our substance if we add so many joules of heat to it? And that depends on the mass as well. And it's all based on this formula. Remember, Q means our heat. And then we have that specific heat capacity, which I think your book uses S, which is fine. And it's a constant for the substance that's being measured. Like water will have a specific heat capacity. Put something else in it, it'll have a different heat capacity. Then the mass of the substance and the change in temperature. Right? So remember, the change in temperature is the final temperature minus the initial temperature. And you always put it in that order. And that means that if the temperature goes up, if it's higher at the end, then this will be a positive value. If it's lower at the end of the experiment, then that'll be a negative value, which is fine because we have defined our terms. What does negative mean? What does positive mean? Okay, usually, well, the specific heat capacity itself is in terms of units of measure, joules per gram degrees centigrade. Those are the units of measure for a specific heat capacity. And all you have to do is just bring that up here and say what happens to them. Well, if the mass is grams, grams cancel because that's in the denominator. And there's degrees centigrade, cancels this denominator. And you're left with joules, which is the unit of heat. Okay? Sometimes, though, rather than grams, we may use molar heat capacity. And the only difference is, instead of grams here, you have moles. So it'd be joules per mole degree C. We might run into that in our lab experiment, using molar heat capacity rather than, we might use both of them actually. Did I hand out a copy of that? That was here during the exam too, wasn't it? Okay, so you have a copy of the upcoming exercise for next week. Okay. Just sort of this is a develop our intuition. If you put two reactants together and they're both at the same temperature, but at the beginning, and then you measure a temperature increase, we can say that the reaction was exothermic because it produced heat. Remember when we had the expression, we have a reactants yield products, and then if it's exothermic, heat's going to be on this side. Right? It's a product. So we put these two reactants together and we get some product plus heat. So that's exothermic. And just the converse would be If it gets colder, that means it's absorbing heat in the process of the reaction. And then the heat is, you can visualize it as the heat being stored in these products. Okay? We'll get past the preliminaries in a minute and on to some actually problem solving. So this is basically what your calorimeter is going to look like. You can buy calorimeters. In fact, I've got a set of store-bought ones. They're just too big. It takes too much reagent to make them work. Right? They're made out of aluminum, and all they've got is an airspace between the two containers, the inner and the outer. And that's not good enough isolation for me. So I went and made some out of styrofoam cups. And they're smaller, so you don't have to use as much. And you have the parts. We have a double styrofoam cup for ensured insulation. And you have a stirrer because you want everything to equilibrate in there, so you got to mix it. And then you have your thermometer. And then whatever you put in it, you know, sometimes it's water. Well, in our case, it'll be water. And you measure a change in temperature. Okay, let me see, did I show you guys this one? I know I showed you this part, system and surroundings. But did I also draw like that? Okay. If we, well, let me start with the system first. There are three approaches to defining this boundary right here. If that boundary is open, then that means we can mass and heat can cross that boundary, right? That's not much use, really. If it's, get my terminology right. Okay, hold on a second. One of them is isolated. Must be closed. If the boundary is closed, that's not right. It's not closed. I'm not trying to think. I hate it when this happens. If I use the right term, then there would be only heat could cross that boundary. And if it's isolated, then nothing crosses the boundary. So the idea is that with our calorimeter, this is a boundary, that's a boundary too. So what we're going to do is, within the calorimeter, actually, we are going to have an open system here. System and surroundings are going to be open, but this is going to be isolated. And that's our styrofoam cup. So everything that goes on, everything that happens in Vegas stays in Vegas. It's inside the styrofoam cup. Okay? So there's our formula again. So let's say we put 2 amounts of water in that cup, and they both weigh the same. They're both 100 grams, right? So that'd be a pretty big cup, 200 mils total. But one's at 90 degrees and one's at 100 degrees. They're They're both water. They're both the same mass. So really the only difference is temperature, right? So intuitively, you should surmise that if one starts at 90 and the other starts at 10, they're going to meet in the middle. So their temperature should be exactly 50 degrees. Okay, that's the ideal situation. But what if you have 100 grams at 9 degrees, but you have 500 grams at 10 degrees? How are you going to deal with that one? Well, let's do it intuitively first. If this one has the most mass at that temperature, this one has the least mass at that temperature, is it going to be 50, greater than 50, or less than 50? Less than 50, right? Because the greater mass has the lower temperature. Now we can actually calculate what that temperature is. Here's how you do it. Inside our isolated system, the styrofoam cups, the total of all the heat changes that occur in that cup is 0. The heat change that's due to one component, say the 100 grams water, is one change. Then the 500 gram water will be that change. And then you can just keep going. However many components you have, just add them all up, and they always equal 0 in an isolated system. Okay? In this case, we're going to have 0 equals, let's take 100 grams first. So if we do, this is going to be mass, specific heat times mass times change in temperature. Okay? So specific heat of water is 4.18. And that's joules per gram degrees C. Then the mass is 100 grams. And the temperature change is final minus initial. So what's the initial for the 100 grams? 90 degrees, right? What's the final temperature? We don't know. That's what we're solving for. We want to know what the final temperature is, right? Okay, so now what happens to the other one? Well, it's water, so it has the same specific heat. Right? But it has a different mass. And the final temperature is going to be the same as this final temperature, right? Because they're in there mixed together. So eventually they're going to come to equilibrium at a temperature. So the final temperature is the same for both of them. But the initial temperature is different. This one's 10 degrees. So there you've got your problem set up. Now all you have to do is solve for that one unknown. Okay? So let's do it. Okay, let's see. This part over here will be 100 times 4.8, which would be 418 joules per degree C, because the grams canceled. Right? And this is going to be TF minus 90 C. How about this one? 500 times, we'll just say, what's 1,000 times that? That's 4,180, and then a half of that is 2090. Anybody checking me on that? Was that right? Okay. Okay, intermediate step. Okay, now what do we do? Well, we've got an unknown and a known in here, so we've got to resolve that figure. So this one is going to be, I'm going to leave the units out because they take up too much space. Okay, 418 times TF minus 418 times 90. What would that be?
$37,620.
Okay. Then this one is going to be 2090 TF minus 20900. 10 times that. Okay. So now we got to get our the unknown figures on the same side of the equation and the knowns on the other side. Well, since we've got a negative here and a negative here, why don't we put these over on this side? Just add those two together. And I get 58520 from these two figures right here. And then that leaves this one plus that one on that side. So I get 2508. Yeah, 2508 TF. Okay, so now TF is just this one divided by that one. Okay, so that didn't work. Try that again. There we go. I get 23.3. Okay, is that what you got? So that is less than 50. We have a final temperature that's, let's see if the slide tells me the same thing. Round it off, okay? That's how you do a calorimetry calculation. It's all dependent on this fact that all of the added up components inside the calorimeter have to be 0 because our system is isolated. Nothing can get in, nothing can leave. Any questions? Any questions from the remotes? Okay. What happened to Julianne? She lose her connection? There she is. Okay. You guys can chime in with questions if you have them. Okay. So if there are no questions about that, we'll go to the next topic of calorimetry. What if the Q, one of the Qs is water, and the other Q is an iron ball? What do we do about that? What's different between those two? This right here. Well, that, plus this could be different, but that's definitely different, right? The iron ball has one value, water has a different value. Now, what does it mean if, okay, so water is 4.18. That's for water. And how about the iron? What is it? 0.45? So let's see, that's joules per degree gram, degree C, joules per gram, degree C. So what does it mean? Well, it means that it takes 4 joules to change the temperature of 1 gram of water 1 degree centigrade. But for iron, it only takes about 1/10 of that, a half a joule, to change a gram of iron by 1 degree C. That's what specific heat capacity means. So the lower heat capacity is the one that can absorb less heat for the same change in temperature. Right? Okay. That's why water's good. That's why having so much of it is good for our planet, because it stabilizes the temperature. Right? If it was just a rock, you know, like the moon, then its specific heat capacity would be a lot lower than water, and its temperature variation would be wild as a consequence. So we could run through this one. You just do it the same way. You set it up with 0 equals Q1 plus Q2. Decide which one is which, Q water, Q iron. Fill in those values. Say which one's unknown. Well, what's the question? Yeah, final temperature. So you want the final temperature of the water. And if you go through and actually do the calculation, you find out that the temperature is 18 degrees. I'm going to let you do that one on your own. Because I want to get to another topic first before we run out of time. We're still talking about calorimetry, though. Oh, we have to. Okay, I'm not going to go to Hess's law yet. I got another point to make, and it's an important one. Because when you look at the lab that we're going to do, the first page is calculate the calorimeter constant. If you looked at it already, you know that. All right, what is the calorimeter constant? Well, it's the factor that we use to take into account any heat absorbing or heat producing capacity of the calorimeter itself. So if we don't take that into account, we might mistakenly think that the heat change is due to our reaction when part of it is due to the calorimeter, right? So even though the calorimeter is an isolating system, it still has a finite heat capacity. It may be very low, it usually is, but you still have to take it into account. So now the equation becomes this one. Say we have a couple of components in there that we're dealing with, and this one is the heat either absorbed or given up when we conduct the experiment for the calorimeter. Okay? So how do we find out what that is? Right? Well, these two are still going to be S times the mass times the change in temperature. But this one, we don't know what the specific heat capacity of the calorimeter is because it's got several components, right? Ours has styrofoam, it's got the wire, it's got the plastic lid, and it's got the thermometer, right? They're all different heat capacities. So the solution to that problem is you combine that term right there. Specific heat capacity and mass is combined into a single term, or C, big C. Okay? First thing you have to remember about doing this part of the experiment is once you set up your calorimeter with a thermometer, a wire, and the styrofoam cups, don't change them. Because if you swap out thermometers, you've changed that value. Okay? Once you build it, keep it there. Because if you build it, they will come. Anyway, don't remember that movie? Okay. So we're going to do this. So that means that this is going to the answer here is going to be in joules. So that means the units here are going to be in joules, degrees C. Because the only factor you have to cancel to get joules is temperature, right? So that means this will be joules, that'll be joules, that'll be joules. And we're all compatible. Okay, so how do we do that? Well, you set up your experiment with hot water and cold water, right? We're going to have some water boiling, and you can use tap water for the rest. Well, not tap water, excuse me. Use distilled water at room temperature, okay? So we're going to have one of them. Say this will be the cold. This will be the hot. So this one's going to be 4.18 for water. And then whatever mass you want, you can choose. You can set the same mass of each one, like 50 mils of each, because we have a 50 mil graduated cylinder. So this could be 50 grams. And we're just going to assume that the density of water is 1 gram per mil. So if you have 50 mils, you've got 50 grams. And then the temperature is going to be, well, you're going to have an initial temperature and a final temperature, right? So the final temperature is going to be whatever it is, right? You will know those values, beginning and end. So you're going to have a final temperature that you will know, and you have initial temperature that's going to be cold. So it'll be room temperature, which would be in the neighborhood of maybe 21 degrees, something like that, okay? Then the hot one is going to be the same specific heat capacity, and we've chosen the same mass, but it's going to be, first it's going to be boiling. Right? Then you're going to transfer that boiling water into your 50 mil graduated cylinder. Then you're going to pour it into another styrofoam cup, a separate cup, and then measure the temperature, right? If you measure the temperature before you put it into your graduated cylinder, it's not going to be the same when you dump it in the calorimeter. So you want to measure it out, put it in your styrofoam cup, and then stick your thermometer in it and measure the temperature, and then take your tap water and your hot water, not tap water, room temperature water, your hot water, put them together right after you measure that temperature, so that you know the temperature going in is as close as you can get it to what it really is. So let's say you've got it boiling at 98 degrees, because we're at 2,500 feet elevation, so it's not going to boil at 100. So say it's temperature. The final temperature is going to be the same for both of them, whatever that happens to be. It'll be between 21 and, say, I don't know, 80 degrees. Because it's going to cool off, right? When you take it out of the boiler, put it in your styrofoam cup and measure it, it's going to cool down. So say it's 80 degrees. And over here, now you've got your calorimeter that's part of the problem. You got that calorimeter constant, which is the unknown. That's the one we're trying to find out, that value right there. And it's going to have a temperature change. So its final temperature is going to be the same as all of these. But what is its initial temperature? Actually, I told you wrong before. Dumping the tap water and the hot water together, you're going to put the tap water in there first, right? And let it equilibrate with the calorimeter, so that the calorimeter temperature is going to be the same as the tap water temperature. Okay, so this will be 21 or thereabouts. Then you put your hot water in and equilibrate it. And when the temperature stops changing, measure that temperature. That's the final temperature for each one. Once you have those values, then the only unknown you have left is this one. Solve your equation for that. Now, I don't know exactly what it'll be because all the components have different heat capacities. Rule of thumb is most heat calorimeters that we use in the lab, if your instructor says don't bother with that procedure, use 10, right? So that's a good ballpark. You know, if you come out with something, you know, within 2 times or half of that or whatever, close to 10, then you know you're in pretty good shape. If you come out with a C value of 5,000, you probably had a math error in there somewhere. Okay. But once you find out what this is, then that becomes part of the calculations for the other parts of your experiment. Because whatever you're doing, whether you're dissolving, let's see, what was it? Sodium nitrate, was it? Yeah, we're going to dissolve a couple of things in there. Sodium chloride, was it? One of them. We're going to dissolve a couple of things and measure water is our starting point, and then we have to include the calorimeter in there. Oh, we're going to have an acid-base reaction too. Remember that. We're going to have a heat of solution, and we're going to have an acid-base reaction. But you have to find out what this is first. Then you can do the other stuff. Any questions? Okay. So now we'll go to the next topic. Hess's law. Remember when I talked about 2 types of processes, or functions actually, state function, path function. Hess's law takes advantage of the characteristic of enthalpy, says it's a state function, the delta H. The delta H is a state function, so it doesn't matter how you got there. Right? You could conduct your chemical reaction, measure the heat, do a calculation, say, okay, so for this one, that reaction uses or produces like, I don't know, 1,000, 2,000 kilojoules, something like that. But if you don't want to do that reaction, you just want to calculate what the delta H is for the reaction, but you do have data on several other reactions, and you can manipulate them so if you add them together, you get the reaction you want. Then you just add up the heats for each one of those, and you get your reaction enthalpy. That's what Hess's law says. It doesn't matter how you get there. You can take all these separate reactions, add them together, manipulate them how you need, then add the heats together, find out what it is. Sometimes we do that just because we're lazy, or sometimes we don't have the money to do the reaction. Or maybe the reaction, you suspect that reaction is going to be extremely violent, but you want to find out just how violent it is before you try to do it. So then you add up these individual reactions and you find out, you know, just how much heat is it going to produce? You know, is it going to be so much that I need to conduct it under a hood, you know, with layers and layers of protection? You know, it's good to know that going in. So here's an example. This just shows that if we conduct this reaction, nitrogen gas and oxygen, and make nitrogen dioxide, then the enthalpy of that reaction is 68 kilojoules. So that's a positive number, right? So that means that it is endothermic. It's going to absorb heat in the process. That's kind of weird, you know, because this is a combustion. Nitrogen plus oxygen yields 2NO2. But that's it. I mean, it's endothermic. We know that because we've measured it. But what if we have these two reactions? Where we only have one oxygen to produce NO, nitric oxide, you know, the one that dilates your vessels, all that good stuff. If we know that one, and we also know this one, if we combine those two, then do we get the reaction that we want? Does it look like that? Okay, two NOs over here, they cancel, right? I think I've got some animation here. Yeah, they cancel. And this one is on this side and nothing else, so it can go down here. You got two of these here, so that means two O2s, and you got two NO2s here. Right? So now we have that reaction based on these two, and these are the heats. This one's extremely endothermic, and this one's extremely exothermic. And when we add them together, we get that value. So that just confirms that we can use this because we actually did that one and then compared it to this method, and we do get the same value. This is just a graph showing that why Hess's law works, because it's a state function. It doesn't matter how you get there, right? One reaction goes this direction, and then the other reaction comes back this way, which is the same thing as going from here to here. It's direct.
Hess's law illustrates why enthalpy is a state function. For example, we want to determine the enthalpy change for the combustion of graphite to carbon monoxide. Imagine that the reaction takes place in two separate steps. Step 1 is the combustion of graphite to carbon dioxide. Step 2 is the decomposition of carbon dioxide to carbon monoxide. The net result is obtained by adding the two steps and canceling out like terms. The enthalpy change for step 1 is negative 787 kilojoules. The enthalpy change for step 2 is positive 566 kilojoules. Therefore, the desired enthalpy change for the net reaction is the sum of negative 787 and positive 566 kilojoules, or negative 221 kilojoules.
Okay. Now we need some rules, because when you've got two or more equations that you want to combine, sometimes they're not written the way that you want them, so that they'll add together and produce the reaction you want. Sometimes you might have to multiply by a whole number or by a fraction, or you might have to maybe flip the equation, right? Put the terms on the side you want. And that's perfectly legal as long as you follow the rules. So when you do those things to your equations, what effect does that have on the enthalpy? That's what you need to know. So if we reverse the reaction, you're just running the reaction in reverse, which means the enthalpy change should be a sign change. Right? If it's exothermic going this way, it's endothermic going that way. So you just change the sign. Oh, there must have been another rule up there. Hold on a second. If you have to multiply by a value, like you need 2 of something. So you multiply the whole equation through by 2. You can't just do parts of it. You got to do the whole thing. So you multiply through by a whole number. That means that the enthalpy is also multiplied by that number. Because if you have one equation, say you have one value of this equation giving you 100 kilojoules. Well, if you do another equation like that, it's another 100 kilojoules, isn't it? Yeah. So if you multiply by 2, you get 2 of them. Then you can add them together. Let's see, I'm going to do 115. And be sure I'm not running out of time. We should be okay. Okay. So we're going to use these two equations to produce this equation and find out what its enthalpy is. First of all, check to see if you've got all the terms you need, right? There's nitrogen in this one. Do we have nitrogen up here? Yep, there's nitrogen. There's water here. There's water. There's oxygen. There's oxygen. And there's ammonia. There's ammonia. Okay, so we have all the terms we need. We just need to be sure we get them on the right side and in the right amounts, right? So we need 2 nitrogens here, right? The nitrogen's on this side, right? It's on the wrong side, so that one has to be flipped, and that makes this negative. But there's only half a nitrogen here, and we need 2, so what do we multiply times a half to get 2? 4. We need 4 of them. We need 4 halves equals 2. So we multiply this, we flip it and multiply it through by 4. Right, so that becomes negative times 4. How about this one? We need 6 waters, but we only got 2. So we multiply this one through by 3. We have to flip it too, because water has to be on this side. So multiply by 3 and flip it, so that means positive times 3. Okay? So let's see. There we go. So now that one's times 4. We've already flipped it. And that one's times 3. We've already flipped that one. So this is what we get out of those 2 equations. Now, when we add them together, are we going to get this? Well, let's cancel terms first, right? We got hydrogen on the right, hydrogen on the left. In the equal amounts, they're gone. That leaves us with oxygen on this side, 3 of them, 4 ammonias, 6 waters, and 2 nitrogens. So now all we have to do is add them together. And when we add them together, we can add these 2 together. And this equation then has an enthalpy of positive 1,268 kilojoules. Okay, just have to be methodical. Walk into a room, check your corners for bad guys, you know, and then do you have the right terms? And when you get finished, do you end up with the right equation? That's the final test. Okay, notice, I don't know if you noticed, but one of those, like this one, had fractional values, coefficients, fractional coefficients. You know, up to this point, we've been saying we want whole number coefficients. Well, that's true. But there's a definition that we have to deal with here. Oop, I went the wrong direction. Come on. Go back. One more. One more. There we go. It's called the standard enthalpy of formation. What does that mean? The standard enthalpy of formation, or delta H little 0 sub F. This means standard conditions, 1 atmosphere pressure, 25 degrees centigrade, and if there are any solutions involved, they're 1 molar. And this means formation. So it's the standard heat that either is released or absorbed during the formation of a compound from its elements. Right? So in that case, you start from the answer, and you have 1 mole of it. Under standard conditions, this is a gas. Right? So now, what does it take to make that from its elements? Well, you need nitrogen and hydrogen under standard conditions, right? So nitrogen under standard conditions is like that, and hydrogen is like that, right? Because they're diatomic. Remember the diatomics? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are the diatomics. So under standard conditions, these are diatomic. Now, you never touch that one. If you're trying to write a standard enthalpy of formation, once you've written this 1 mole of it, don't touch it again. Everything else now happens on this side. That's why sometimes we have to use fractions. So how many of these does it take to make 3 of those? 3 halves, right? A half of this one is 1, right? And then 1 times 3 is that. How about this one? Half of N2 is N, and then N times 1 is 1. So we have a half of this one, 3 halves of that one makes that one. That's the form for standard enthalpy of formation. Okay, you have to start with the elements in their standard states and end up with 1 mole of compound. Okay, I already said that. Okay. This is the author's idea of explanation. I think it's got too many arrows and too many colored balls. Just remember that when you reverse the reaction, you change the sign on your delta H. And when you multiply the reaction times a number, whether it's a whole number or a fraction, it could be either one. You multiply that same number times the enthalpy. So if we have, usually it'll be this way, and then you'll have the enthalpy over here, in this case of formation. Just do this. If you have to multiply that whole thing through a number, just include your enthalpy value in the brackets, and then put your multiplier out here. Then you'll remember to do the whole thing. Say we just need 2 of them. So then it's 2 times this one, 2 times that one, 2 times that one, and 2 times that one. Okay? Now there's one other way to arrive at the enthalpy. If you have an equation and you also have access to the standard enthalpies of formation for all the compounds in that equation, you can use those standard enthalpies to calculate the standard heat of the reaction. Okay? You just use this formula. You need to know the sum of all the standard enthalpies of the products and then subtract the standard enthalpies of the reactants. I think they're going to give us an example to work with you. Okay, here we go. So we have the balanced equation, 2 sodiums plus 2 waters yields 2 sodium hydroxides. That's aqueous solution plus hydrogen. Okay? Now, if we're going to use that summation, we need to remember 2 rules. One is, and this is a good rule, if you have any elements here, they don't count. They're 0. Right? All standard enthalpies of formation of elements are 0. So you don't even have to look at those. You just look at this one and that one. So we'll take the standard enthalpy of this one and subtract this one from it. But you also have to consider the coefficients. Remember, because the standard enthalpies are for 1 mole of each compound. And if you have 2, then you got to multiply. So the standard enthalpy of sodium hydroxide is minus 470. 2 times that one. Then you subtract 2 times the one for water, minus 286. Right? That's your delta H under standard conditions. And that should resolve to minus 368 kilojoules. Okay? Pretty simple. Just got to remember, do it methodically, step by step. Be sure that your equation is balanced first. If you're, well, on a test, if I'll tell you it's balanced, then you can believe it. But if you're a natural-born skeptic, you may want to check it anyway. Okay. So those are all the topics that you're going to need to solve problems in your review documents. The rest of this is keep the socially conscious authors happy. What are our forms of energy that are available to us? You know, well, fossil fuels, right, which are get a bad rap, I think. Then there's wood. Wood's not a fossil fuel because it's constantly growing. Fossil means it's buried in the ground. So that means oil, natural gas, and coal. Then there's hydroelectric power, right? There's only just so much of that because the places that you can access hydroelectric power are limited. You need enough change in height so you can build a dam and run a generator. Then there's nuclear. Nuclear power has gotten a bad rap too. It's not as dangerous as they say it is. But the regulatory process is so cumbersome that we haven't built any new reactors in this country for decades. But if you want to cut down on carbon dioxide emissions, nuclear is the way to go. So if anybody comes up to you and says, starts screaming in your face, which is usually what they do, that carbon dioxide is a pollutant, we need to get rid of all of it and say, okay, how do you feel about nuclear? If they don't want nuclear, then tell them shut up and get away, because that's the only way you're going to solve it. There's not enough energy in hydro, or we left off wind, hydro and wind, to drive the world's economy. It just does not exist. We need nuclear. And before we catch up with nuclear, we're going to have to use a lot of this to get there. So that brings me back to the topic of CO2 as a pollutant. That argument is just ludicrous on its face. I know the EPA has been trying to list CO2 as a pollutant for years, and Congress won't let them do it because it's stupid. I mean, there are peer-reviewed publications on the increase of CO2 in controlled environments. What effect does it have on plants? Well, it makes them grow more. Yeah, you get more productivity with higher CO2. So that's one aspect. You can look at the history of the Earth. You know, how do we get all these coal beds and oil beds deposited? Well, at one time, the productivity of plant life on this planet was hundreds of times more than it is now. I mean, there was so much that the natural decomposition process couldn't keep up. So they got buried. Now we have coal. So at one time, the Earth was a lot hotter and a lot more productive. And it could be that again. And it needs to be that way if we're going to feed the growing populations. Okay. So this is just a chart of how we've progressed from wood and coal in the 1900s, and then gas and oil took over, and then hydro is it started off a little slow, and then it's kind of leveled off. So we're back to the point now where natural gas, I think, is taking a large part of that. Actually, there ought to be a 2010 in there, because there have been significant changes recently in the use of natural gas. As far as CO2 production goes, natural gas is more efficient, produces less CO2 for the same amount of energy output. Okay. Oh, and don't get me started on ethanol. It takes more energy to produce ethanol than you get out of it. Right? There wouldn't be any ethanol in your gasoline if it wasn't for government subsidies. What's the saying? If you want more of it, subsidize it. If you want less of it, tax it. Right? Okay, so the Earth's atmosphere is a valuable commodity, right? It's got oxygen that we need. It's got CO2 and nitrogen that plants need. Now, most plants, no, all higher plants cannot access the nitrogen in the air. They need it to produce proteins and nucleic acids. So they form symbiotic relationships with microorganisms that have the enzyme systems to convert into ammonia and nitrates. Right? You just pull up any legume like clover, or if you're close to a farm, we don't grow soybeans in West Virginia, do they? Not much. But if you ever get a chance and yank up a soybean plant, and they've got little nodules on the roots, just take your knife and cut into them. If they're pink, then they're producing. They're taking nitrogen from the air and fixing it for the plant. It's a symbiotic relationship. So the atmosphere's got that. It means it's got 79% nitrogen, it's got 20% oxygen, and then it's got, let's see, maybe 350, 380 parts per million of CO2. And it could go higher. It probably will. And that's not a bad thing. I mean, of course it is for Al Gore, because he can't stand up on his soapbox and make lots of money. Or fly his jet around the world. That was funny. Well, they had that climate conference over in Europe just recently, right? And everybody going to the conference arrived on a jet plane. Okay, you gotta laugh, otherwise you cry. But what happens is radiation from the sun strikes the earth. The upper ozone layer absorbs the harmful UV rays, a lot of them. And the other visible light reaches the ground. Some of it is absorbed by plants. Some of it is re-radiated at a lower, longer wavelength. Infrared is common. And that does not escape into the, they say some of it does. Most of it is captured by the atmosphere. And that's what keeps the surface of the earth warm. But as far as efficiency and amount, the greatest greenhouse gas we have in our atmosphere, water vapor. So it depends on what form it's in. If it's just water vapor in solution, then it will absorb re-radiated energy. But if it's in the form of clouds, does the opposite. The light coming in gets reflected. So that's what those contrails, everybody worry about the contrails from jet planes. There's enough of them, you get reflection back into space, the light that's, the energy that's hitting the earth from the sun. So I just wish they'd consult a bona fide climate scientist when they start writing these reports. They claim that there's a consensus. Oh, that's another issue. Science. Science and consensus don't meet ever. A science is in constant flux. You never reach a consensus. You have some agreement, and then you move to a higher level. But that lower level can always be changed, right? No such thing as consensus in science. So when they tell you that 100 scientists agree, blah, blah, blah. Well, maybe they do, but they're not scientific when they do it. Okay, new energy sources. All right. There's been research on converting coal into other forms, like natural gas. And of course, in the process, you create waste. What do you do with the waste? You know, you've got ash, and you've got probably some CO2. So you got to do something with that. One of the things is it has to do with the efficiency of methane combustion. Produces less CO2 in the process. And the other thing is, if we're ever going to run on fuel cells, we've got to have a source that can go into the fuel cell, do its thing. It acts like a battery, of course. And methane fuel cells are in development. They're becoming more and more efficient. So methane would be a good choice. Actually, the best choice, if you could develop the infrastructure for it, is hydrogen. You just take hydrogen as your fuel, oxygen from the air, combine them in your fuel cell, and you're off and running. Problem is, historically, fuel cells have had to operate at very high temperatures, extremely high temperatures, which makes them unsafe. The ones that they used in the Mercury, Gemini, and Apollo space program were very hot, but that was the most efficient way. They already had the oxygen there. They already had the hydrogen there. So why not use a fuel cell?
So does it mean when you have a nuclear plant, you always have to have a source?
Oh, for cooling, yeah. Right. You have to have a way to cool it. But that's true of any large power plant. You have to have a way to cool it. Air is not the most efficient. The specific heat capacity of water itself, that 4.18, is a good value for absorbing heat. But even more than that is the latent heat of vaporization. So how much heat can water absorb when it goes from liquid to gas? That is huge. It's like at least 25 or 30 times that 4.18. So that's what the cooling towers are for. Hydrogen as a fuel, that would be great. I mean, if we have nuclear plants that produce no chemical pollutants, I mean, you could consider heat as a pollutant. But you can use that energy to split water into hydrogen and oxygen. And then you could use the hydrogen as your fuel. And then when it recombines with oxygen, you just get water. That's it. That's the Holy Grail. Well, not the Holy Grail. That's an intermediate grail.
Well, if the U.S. does pick up this to do that, so the U.S. do that.
Could be.
Water, lots of space.
Water, yeah.
Government.
Yeah, they wouldn't want to do it out west. Not enough water. Oh, the Holy Grail is fusion. Fusion energy. We've got plenty of deuterium and tritium in our oceans. And if we just figure out how to fuse them together, get the energy, then that would be even more valuable than fission reactors, where you split the uranium or split plutonium or whatever. Thorium is a good candidate too. It's safer, in fact, than uranium. Anyway, then we have the oil shales and oil that's trapped in formations that we couldn't get at for many years. Now we have the technology called fracking, where we can get at gas pockets, we can get at oil shales, all these. That's why the U.S. now is a net energy exporter, because of fracking. And that's good for the economy. And it's good for the free world. Right? The less free countries have to depend on totalitarian countries like Russia for their energy, the better. Or Well, Iran's not an issue right now because we got them boycotted. But maybe Venezuela will come around. They're trying. They've got more oil reserves than Saudi Arabia. They just had a dalliance with socialism and it's killed their economy. Maybe they learned their lesson. Just one generation away from falling back into socialism, I guess. Okay, next time we meet, we'll do reviews. And I'll get this converted and on Blackboard as soon as possible.
We don't have class names to be burned for the spring break.
Oh, that's right. Next week is spring break, isn't it? Okay, so the Monday we come back will be a review. Then a Wednesday will be an exam, followed by a lab. Yeah. Let's see. What are we sure? Does anybody need copies of these things?
I gotta listen to the lab.
Need a lab? Okay. Calorimeter. Let me see if this got everything I need.
Yeah, I need the lab too.
Yeah, there's a calorimeter constant.
Hey Tyler, will you pick me up a lab too?
I might not be for spring break. I might go down to where I'm from.
Oh, really?
South Carolina.
Okay.
That's where you're from?
You're going to give that to Coach? You think he'd mind if
Yeah.
I give his,
You guys, class dismissed.
just don't look at it.
The active one's the one I took down.
Hey, Dr. Bly, are you gonna have the lab posted to Blackboard?
Say again?
Are you gonna have the lab posted to Blackboard to where you could just print it out?
Yeah, it should be on Blackboard now.
Which one is it?
Calorimetry.
Great, I should be able to find it then.
Okay, if you can, email me and I'll attach a copy to you.
Okay,
3,000.
Okay?
if I can. Only if I can.
Okay, that's fine.
And I apologize if I seem a little distracted. I had my little boy and my little girl trying to demand attention.
Oh yeah, been there, done that. Now I have cats bothering me all the time. Y'all have a good one.
When you leave
See
them
you after the
alone.
break.
I did build a nuclear plant from all the satellite dishes.